Hello, physics students. I had some students ask for some more traditional sort of, I think, lessons and some notes. So if you look in the Google Classroom, there are some notes you can print out and write down stuff along with this. So it won't be the video won't take as long as a normal class period. But so you're going to have to stop the video to take down the notes. Fortunately, we've been through a good amount of this stuff in other formats in YouTube videos and things like that. So hopefully, even though this is a video and not in class, hopefully you will be able to understand the material. So this is the PowerPoint I may have used in class. So objectives. Today, we're going to define and describe electricity, current, resistance, and voltage, and to be able to use Ohm's law to predict the change in current based on a change in voltage or resistance in checking for understanding questions and practice problems. Okay, so we're going to learn about electricity, current, resistance, voltage, and Ohm's law. So I had a question I would have asked you. How would your life be different this month if there were no electricity? What wouldn't work and what would you have to do differently? So particularly this month, that would mean no school because we're on social distancing. So no electricity would mean no internet, right? Would mean, I don't know if you've ever been in a blackout, just the power's out for a while, and how many things require electricity. Your phones will die after a while, computers, but even things like your refrigerator, you start worrying about the food going bad. I don't know about you, but it's quick and easy for me to realize that certain things don't work. Oh, the stove doesn't work, right? So I'll just use the microwave. It doesn't work either. Things like that. So we rely on electricity a lot in our lives these days. But what is electricity? What is it really? People knew about things to do with electricity, but without even knowing what it was. So I'm going to show you here a little simulation, okay? And it says the electricity we often experience is due to the movement or flow of electrons, okay? So I'm going to go to this here, and here is a little setup I have, okay? And so this is supposed to be a battery. This is a little switch. I can open it or close it. And there's other switches here. These are little current meters, okay? But particularly what we're going to do is I'm going to show the current. So if I show the current as electrons, that's what's really happening. Then they have these minuses. Now really there should be a bunch of them all packed together, but they just kind of represent them as, they're separated like this. And conventional current, before they knew anything about electrons, conventional current looks different. Okay, so if I turn this on, this is the, so I put this switch, but see, nothing can get around, okay? If I flip this switch, these light bulbs turn on, and we see, this is the positive side of the battery, but see that they're showing the arrows of the current going around this way, up through the bulb, up through this other bulb, and around. Now, why is no electricity going through this light bulb? Well, because the electricity cannot get from the positive side of the battery around to the negative side of the battery because our circuit is broken right here, right? Now, in reality, it's not positive charges moving. They just guessed. Let's just, back in Benjamin Franklin's day or soon after, they said, let's suppose positive charges move. We can't tell if it's positive charges moving around this way, which would be what? Kind of a counterclockwise direction, or if it's negative charges going the other direction. It really is negative charges going the other direction. But you can see all these wires already have electrons. All these pieces of metal have electrons that are free to move. But these guys are not moving because there's no way for them to get around. So like if this were a water pipe and there's just a closed pipe here, the water would be sitting in the pipe, but it wouldn't be moving. But if we connect this, then charge will start flowing. The electrons will start flowing through this as well. So what is electric current? Electric current is a movement of electrons, okay? And you can see here that the currents through here and the current through here is different. They've animated it this way. These electrons, you can see if you were to count, how, 1, 2, 3, 4. If you were to go down here and start counting, it'd be 1, 2, 3. It's longer, right? The current is, there's less electrons going by every second. Now, really, these numbers, these electrons are representative of much more charge than just one electron. But current is a movement of electrons. So if I were to just, before this video, yesterday somebody asked you what's the first thing that comes to mind when you hear the word current? Okay, so what would you think of when you hear the word, what do you think of when you hear the word current? Well, for most of you, I'm guessing the first thing that comes to mind is some kind of water, something to do with water. So a river, something like that. So what kind of units would we use to measure water current? So think to yourself, what kind of units would you use to measure a current? Like scientific units, we're going to measure the current. Well, students often say things like meters per second, right? How fast it's going. Well, that's important. But what if it's a little trickle of water running, going really fast? Like it's a small little stream, but it's really steep right there and the water's moving fast. That wouldn't make it actually a big current, right? If the parents are worried about their kids getting swept away by the current, it's not going to be some little stream, even if it's moving fast. So it's going to be something, a bigger stream, right? But what if the big stream is moving really slowly, right? It's hardly moving. You're not going to be worried about your kid getting swept away in the current. So it has to do with both. It basically, current, you would measure if you were like a water engineer and you're figuring out how much water is going by in this river, you'd be measuring something like how many kilograms of water are going by every second, or maybe how many gallons or liters of water are flowing by any particular spot in the river. You'd set up a little thing. It takes the water as it comes by and measures how much water is going by every second in liters or gallons, or you could do in mass and kilograms. Okay. So for an electric circuit, instead of water going by every second and measuring it in kilograms or liters or something per second, we're going to have charges going by, all right? And the circuit, through our circuit at any point. So electric current is the rate. It's how much, a rate is how much in how much time. So it's a rate of flow of charge through a location. Okay, so pick a spot right here, say, and measure how much charge is going by in a given amount of time. So a rate means a how much and how much time. So charge, right? Here's our symbol for charge, and we're going to use I use a big Q just so you realize we're not talking about like one little charge that's moving like we had before when we had the electric force was K Q1 Q2 over R squared. This is not a little q. This big Q is representative of all the charges moving by the location, say this spot in the wire, in a certain amount of time. So we'll measure charge in coulombs, and we'll measure the time in seconds, okay? And 3 lines means this is equal by definition. We're going to use a symbol of I for the current, okay? So there's an equation. The current, by definition, is how much charge goes by in a given amount of time, through some location. Like you have a little measurer here measuring how much charge goes by every second, where I is the current, Q is the total amount of charge moving by, and T is the time. Okay, so if we were to look back here at the simulation, then these things here are measuring the current, right? The electric current. It's measuring how much charge is going by every second. They're moving, in the animation, the electrons are moving faster. That's not exactly quite the way it works in a wire probably, but 1.35, where this is 0.9 and this is 4.5. And we'll talk about this more later, but because these two come together, right, the electrons here are coming together, more electrons are going by every second through here than are going through there or there. So in order, this has the most current, this location has the highest current, this has the next highest, and that has the third highest current. So going back to the PowerPoint here. So another way of saying this is current, which we write with an I, is how much charge related to how many electrons, right? Charge is related to how many electrons is going by every second. So current is how much charge is going by every second. a coulomb of charge, and this has nothing to do with circuits. We could have done this last unit. If you take 1 coulomb and convert it into number of electrons, a coulomb is 6.25 billion electrons, or 6.25 times 10 to the 18th electrons worth of charge. Okay, so if the current, I'll say this, and a current is measured in coulombs per second, but we give that a new name. They're called amperes, written with a capital A, and almost nobody says amperes. They shorten it to amps. So technically the unit is amperes, but everybody says it's 5 amps. Nobody says 5 amperes. But if 1 amp, if the current is 1 ampere, or 1 amp through this location, that means a coulomb of charge is going by every second, which means 6.25 times 10 to the 18th electrons are moving through that location in a second. So if you look at these representative electrons, these are representative of many electrons, 1.35, times 6.25 times 10 to the 18th electrons are going through here every second. Okay, that's what that amperes means. So if the current were 1 amp, then a 6.25 billion electrons would be going through this location in a second. Okay, so that's what current is. So what is resistance? All right. Well, I gave you an analogy before, analogy of an air. I gave the analogy of trying to blow air, an air current, through straws. Okay, and I gave you these 3 straws to look at and said if you were going to put these, in your mouth, which would be the easiest, which would be the hardest to blow air through. Okay, now just based off of their diameter, the bigger the diameter, the easier it would be to blow lots of air through a certain location in a given second. So, suppose I'm looking right here. If I blow through this one, it's going to be easier for me to blow air through that through this tube because it's bigger around. So the current it'd be easier to have a high current here than it would be to use a smaller one. So something's resistance is it's keeping it from happening. So this would have a high resistance to airflow because it's just thin, and this would have a small resistance to airflow. It's going to be much easier for me to blow air through a bigger tube. Now, if I blow very gently here and blow very hard here, I could have the same current, right? This one would take a bigger push, right? And so for electricity, you can have a high resistance, but a high voltage and get a lot of current still. But it's going to be easier to have a higher current through things with a lower resistance. And if I want to show you a picture that you should have looked at in your book, this picture here. So the electrons, as they go through their, say metal or whatever they're going through, they'll run into atoms, right? So they're not showing the atoms here. I gave you the analogy of Plinko. If you remember the Price is Right game I showed you in class, the electrons are trying to go through, but they run into these atoms as they bonk their way through the material. And as they run into the atoms, they can speed up the atoms. So the electrons getting pushed this way. There's actually electric field is in the opposite direction. So there's a plus over here, right? The electric field goes from plus to minus. So it's getting pushed away by the minus and toward the plus. And it's getting pushed this way. And as it runs into the atoms, it can speed them up and warm up the material. But the material has a resistance because it's not real easy for the electrons to make it through. Now, if you remember last unit, we did talk about superconductors briefly, and the electrons, even when they run into atoms, they will not speed them up. And I'm not going to go back through that right now. But everything but superconductors has a resistance to electricity flowing through them. And that resistance is based off of several things, partly what it's made out of, is it copper, is it zinc, or what it is, but also just based off of its shape. The thicker the wire, the lower the resistance, and the longer the wire is, the more resistance there will be, because the electrons have to take a longer path of bouncing around to make it through that whole piece of wire. And we can get into more of that as we go along. So going back to the PowerPoint here, a resistor is an object that allows but resists electric current from flowing through it. Okay, so the basic idea is this. If you could just change something's resistance, or you take a resistor and you switch it out for something with a higher resistance and put it in the same circuit would the current go up or would the current go down? Well, a resistor resists electricity. If we flip back over to the simulation, I thought I could, oh, there it is. I just click on this guy. Go away, sorry. Click on this and I can change the resistance. So watch the current. As I make, it's 10 ohms right now is the resistance. If I make the current go, the resistance go up, the current goes down. Okay? And particularly, if I were to go back to, I think it was 10 ohms here, it was 0.9. Okay? Now, it matters that this light bulb is only connected to just the battery. The electrons, it's connected only by wires. There's no other light bulbs in the way of this, but you'll get the general idea here. In fact, I'm just going to turn this one off. There's a switch here. I'm going to open this switch and now these light bulbs go out. Okay, so this current is the same as that current. And I'm going to take this resistance and I'm going to make it go from 10 up to 20. And the amps, the current, goes from 0.9 down to 0.45. So if I take this guy's resistance and double it, and it's the only thing in the circuit, then the current will get cut in half. So they're inversely proportional. If it's the only thing in if it's the only thing in the circuit, this is the total resistance. If you double the total resistance, then the current will get cut in half. Okay, so there's an inverse relationship between resistance and current. So going back to our slide here, resistance is based on the object's chemical makeup, including how many free electrons it has. That's like, kind of how many electrons in that valence shell that are not bonded to other atoms and are free to move. We talked about that last unit. We talked about how diamond doesn't really have electrons that are free to move, but graphite does. So your pencil, quote unquote, lead, your graphite is a decent conductor. So it depends on what it's made of, its shape, like particularly how thick in diameter it is, and its temperature also matters. And we talked about this some last unit, but if we go back to the picture in your book here, imagine there are these atoms here, and we talked about what would happen if you speed up these atoms. Now, I'm not talking about the electrons warming up the atoms. I'm saying just suppose you get a heater out, and you take these atoms and you warm them up. Well, they're going to bounce around faster. Oh, it's hard to show that on this screen, but as these bounce faster, it's going to be harder for this electron to get through. It's going to have more collisions. So my analogy was, in class we used Plinko from Price is Right, or we said imagine we take out all the desks in the class and one person tries to close their eyes and walk through the classroom, and everybody else is in the middle of the classroom, and they start running around with their eyes closed, running into each other, and running into this person trying to walk through. Well, if everybody's walking very slowly, this person is going to have less of a chance to hit them, or more of a chance to make it through. But if somebody's running around, they're kind of covering more ground, if you will, and it's more likely this person will run into somebody. So for metals, which are already good conductors, if you heat them up, their resistance actually changes. Okay, so for things that are metallic, as you warm them up, their resistance tends to go, I'm sorry, I might have said that wrong. As you warm them up, their resistance tends to go up. Sorry if I said that wrong just a little bit ago. So as you heat them up, there's a less electricity, or a smaller current going through, because it's harder for the electrons to make it through that warm piece of metal. And that is particularly important because light bulbs, old style light bulbs that have a filament in here, they glow because they get hot. So it turns out that a light bulb, if you try to measure its resistance when it's off, like if I were to hook something up here and measure the resistance, it's just a wire, and the resistance will be very low actually. But when it's on and it's hot and glowing, its resistance will measure much, much higher. So a light bulb is not really an ohmic resistor. You read something about that, but we'll get to that later. But if you have a very, very, very small voltage, this thing will not be very warm. The light, you won't even see any light coming off of it, and its resistance will be less. Its resistance will be much smaller when it's cold than when it is warm. Now, I mean, I guess you could take a circuit, and throw it in the freezer or something like that. But people don't tend to do that. And it wouldn't change its temperature that much because the electricity passing through it is going to try to keep that temperature really high. But for metals, as the temperature goes up, its resistance goes up. So actually, this is a slide from last unit when we were talking about what conductors were, and I gave you this picture of these electrons in the metallic bonds. The metals bond by metals bond with each other, even if they're copper or gold and zinc, and you can make a wedding ring. Many different metals in there because they bond to each other by sharing their valence electrons all together. So imagine this electron is trying to zip through this way, but it's running into these atoms. And if these atoms are going faster and moving around faster, it's going to be harder for this electron to make it through, so the resistance will go up. So in your own words, what is electric current and what is resistance? So stop the video here. How would you describe in your own words electric current? So if I were just going to say it off the top of my head, I would say current is, a flow of charge. It's a flow of electrons. It's really a measure of how much charge goes by a location or through a location in a given amount of time. So you could say it's the number of coulombs of charge that go by every second. It's a rate of the flow of charge. Usually that charge is electrons. The charge carriers are electrons, but it's how many are going by in a second. It's a measure of how much charge is going by every second or in a given amount of time. What is resistance? Well, stop the video. What is resistance? How would you describe it? Well, resistance is really a measure of something's, how much it kind of prevents or keeps electricity from going through it. It's a measure of how much the material does not want or is not good at letting electricity go through it. We've got one more to do here, voltage, okay? An analogy of voltage, we're going to start with the analogy, and I used this before, but that it's like a water pump. Pumping electrons around the circuit like a water pump moves water in the pipes of a fountain. So this battery has a voltage. Right now it's 9 volts. And so the electrons, as they move from over here and go around the circuit and come to the other side of the battery, they were losing energy, and they give their energy to do stuff like make this light bulb turn on. But you can think of this sort of like the water pump. There's these pipes full of water. The water pump doesn't store water, right? It just pumps the water around. Now, of course, batteries are made of atoms. They have electrons in them as well. But it's not like the battery's this big, water tank, right, of charge. It's just pumping. It has the energy to pump the water around or pump the electrons around when there is a way for the water to pump around all the way around. So voltage is really how much electric potential energy, and you could say each electron or each coulomb of charge, voltage is really related to how much electric potential energy each electron has at a location, at a given spot. And the change in voltage, which is what we really care about, the delta V, is how much electric potential energy it gains or loses per coulomb of electrons as it goes from one place to another. Okay, so you can think of voltage like it's a measure of how much it's related to how much electric potential energy an electron would gain or lose as it goes from one spot to another. So when I look at this battery and it says 9 volts, it means that is a measure of how much energy each electron will lose as it goes around. But volts really isn't per electron. If we wanted to get the energy an electron loses as it goes around, we would take this 9 volts and multiply by the charge of an electron, which is 1.6 times 10 to the negative 19 coulombs. So this is not how much, it's a measure of how 9 volts is how much energy a whole coulomb of electrons would lose. So imagine I've got a big bag of electrons and there are coulombs worth of charge. How much energy would they lose as they go around the circuit? They would lose 9 joules of energy. So 9 joules per coulomb that gets pumped around this circuit. So the voltage is defined as this. A change in voltage is the change in electric potential energy per charge. It's the energy per coulomb. So a volt is how many joules a coulomb of charge would gain or lose when it moves from one spot to another. Now, when electrons go from the minus side of a battery to the positive, that's the way they want to go, from the negative side around to the positive side. They will lose energy. You could actually force the electrons to go the other way, from the positive to the negative, and they would gain energy. But that would be, that's kind of how you charge a battery, is you force the electrons, you bring in some other power source and force the electrons to go the way they don't want to go, and they increase energy, and they will charge up your battery. So that's the equation for voltage. We're not going to worry a ton about this, but you need to have it kind of as an idea in your head of what voltage is. It's related to how much energy those electrons, are losing per coulomb of electrons that you're moving around. In our case, the electrons will go from the battery around the circuit and back to the positive side of the battery, from the negative to the positive. And the potential energy that gets lost is transferred to other forms of energy. For instance, things get warmer. A light bulb could turn on. You can move a Tesla down the road, right? Teslas are electric cars. So they use an electric motor, and the electricity ends up being the reason that the car ends up going down the road. So question for you, what is voltage? How would you describe it? And what is it similar to in a water fountain? So pause the video first. What is voltage in a science way? So give me a science description. So voltage is how much energy and an amount of charge gains or loses when it moves from one location to another per the amount of charge. So it's a measure of how much energy a coulomb of charge would gain or lose when it moves from one spot in space to another spot in space. What is it similar to in a water fountain? Well, the analogy is it's like a water pump. It's kind of like the pressure, if you will. I should say the battery is like a water pump. The voltage is kind of like the pressure in the from the water pump pushing the water around the through the pipes. So what would happen if we increase the voltage in our circuit? Well, that's going to be similar to increasing the pressure. So suppose the pump is providing a bigger pressure through this right here, right? If this is providing a bigger pressure, so if I increase the voltage here, watch what happens to these currents. As I increase the voltage, the current gets bigger and bigger and bigger, and the analogy is, well, it's like we're pushing harder, right? And that's sort of true. It's really that we're giving more energy. If the voltage is higher, then each electron that goes around is losing more energy. So if it loses more energy, then it's kind of when you increase the voltage, you're actually putting a bigger electric field in these wires. They're actually, the electrons are getting pushed harder is really what's happening inside those wires. And since they're getting pushed harder, they're getting more work done on them, and they are going to have more energy available to make the light bulb get brighter up here. If I make the voltage go back down, that light bulb gets dimmer because there's less electricity going through it, and the wire is not as warm. When I go like this and more current flows through there, the light bulb is going to heat up more and become brighter. So is the current a constant? Okay, does current in a circuit have to stay constant? Well, I just showed you that in that simulation it does not have to stay constant. Does the current in a circuit always have to be the same? No. You could change the current based off of two ways. You could mess with the resistance, or you could mess with the voltage. So if the resistance becomes bigger, well, the current, the flowing stream of electrons going by or through that location every second, well, should it get greater or smaller? Should the current go up or down if the resistance gets bigger, the total resistance of the whole circuit? Well, resistance means how much it resists electricity. So if the resistance goes up, it should be harder for the electricity to pass around, and so the current goes down. Okay? If the resistance gets bigger, the current gets smaller. What if we give the electrons more energy as they start their journey? What if we push harder? If we give it a bigger voltage, if the battery has a bigger voltage, then the electrons will have more energy from start to finish. And that's kind of like pushing harder. Will the current get greater, be greater or smaller? Well, I just showed you in the simulation, if we make the voltage higher, then the current gets bigger. Okay? So for many electronic components, not all, but for many electronic components, it works like this. The current is proportional to the voltage. If I double the voltage, the current doubles. Okay? And if you make the resistance double, if you make the resistance double, the current gets cut in half. So the current is proportional to the voltage, but inversely proportional to the resistance. And with the right units, we turn this proportion into an equal sign. If we just come up with a new unit and make the constant, remember, to turn a proportion into an equal, you insert a constant. If you want the constants to be 1, you just choose new units. For resistance is what we're going to choose new units for. And we get V equals IR. You could do I is V over R. That's really the more truthful way of saying it. The current is a result of the voltage and the resistance of the circuit. But we don't like divided by symbols, and it's gotten written like this for 100 years. So V equals IR is a famous equation. And that's called Ohm's law. Now, what you need to realize from the reading is Ohm's law is not always true. It's just true for many electronic components. It's really not actually true for light bulbs, because if you put a bigger voltage on the light bulb, even though the simulation had it work perfectly, a bigger voltage on the light bulb will make, if I go back here, a bigger voltage, if I change this, and this light bulb gets brighter, it gets brighter because it got warmer, and really its resistance should change. So it says 20 ohms here, and when I go like this, it's still going to say 20 ohms because this is a simulation. In real life, the resistance goes up as the voltage goes up, but the simulation doesn't account for that. So light bulbs don't really obey Ohm's law, even though a lot of times we ignore that in physics classes because you're just so familiar with light bulbs. But this is Ohm's law. It does work for a lot of electronic components, like the resistors, the little peanut-looking things I showed you before. For many electronic components at constant temperature, see, that's important, the voltage across the component is proportional to the current through it. So the voltage is proportional to the current if the resistance is, staying the same in the meantime. And that's known as Ohm's law. It's really a delta V, because a voltage depends on moving from one location to another and how much that voltage changed. But people just end up writing V equals IR. Most of the time they ignore the delta and say, well, of course, it's moving from one location to another. It's got to be, going from one place to another through the circuit, or it wouldn't be changing. If it just stays in one place, it's not changing energy at all. So the delta V is the voltage drop, actually. Okay, so if we imagine and go back to this circuit over here, and I'm going to change this to where we're going to go back to conventional current. Okay, conventional current pretends that positive charges are moving. All right, and so if I were to use this voltmeter, I will measure here 90 volts, because that's the battery. Okay, and the voltage is actually going down if you go from one side to the other. So if we imagine positive charges are moving, they're going from 28 volts right now down to, or close to 28. It's a little less than 28 actually, because the wires actually have resistance. If I go over here, I can change this to actually make, giving it a little bit of resistance. So this will be close to 28 over here, and this will be close to 0 volts over there. This is a 28 volt battery. And so the voltage will go down from one side to the other. If I connect this, you'll notice that this side will be, from here to here, will still be that close to 28 volts. And I'm actually going to make the resistance even smaller, so close to 28 volts. This was the resistance of the wires. I know it's off your screen. But now if I go over here, is it still going to be 28 volts? And the answer is no. Okay, so the voltage goes down. These pretend positive charges lose energy going through one light bulb, but they have to lose energy going through the other light bulb too, right, to turn it on. So these guys are going to share the voltage. From side to side is about the 28, but each one of these is going to get, if they're the same light bulb, half of that. So we'll talk more about that later. But my point is, this is really actually, it's really a negative number, okay? Because the if we imagine positive charges are moving, the voltage is going down so that the positive charges will lose potential energy. Electrons actually like to go from the minus side of the battery around to the plus side of the battery. They like to actually go up in voltage. But everything in circuits is defined as if positive charges are moving. So it's often called a voltage drop. It's how much the voltage goes down, so technically it would be a negative change in voltage. But we don't want to work with negative numbers the whole time, so we just call it a positive number, like an absolute value. It's how much the voltage goes down. I is the current in amperes or amps. R is the resistance. And the resistance is a constant for a particular electronic device at a given temperature. Okay, it's, has to do with the thickness of the wire and, it's what it's made out of and things like that. The units for resistance are ohms, after Mr. Ohm, and they gave that the symbol omega, I believe, just because his last name was Ohm. They chose an omega. Maybe if his last name had been, Alpheus, they would have used an alpha or something like that. But that's our symbol, our new unit, so that this constant of proportionality is a 1. We don't have another number in there. We're going to define a new term, a new unit, the ohm, where the ohm is just a volt per amp, or actually, if we come over here to the paper, a volt, this is measured in, I'm just going to put parentheses, these are just the units. Volts, amps, and they're called ohms. A volt, though, is a joule per coulomb, if you remember, because delta V was the change in electric potential energy per charge. This could be a capital Q, that would be okay, but this is joules per coulomb. And an amp is coulombs per second. So what is an ohm? If we multiply both sides by seconds over coulombs, so that these cancel out, seconds over coulombs, seconds over coulomb, and ohm is a joule second over coulomb squared. So that's why nobody worries about it. But we're going to define this new term, an ohm, which is a joule second per coulomb squared. And that allows our constant of proportionality to be 1. Okay? So not all resistors obey Ohm's law. A resistor that obeys Ohm's law is called ohmic. And some things are not ohmic. In virtually every problem, a resistor's resistance will be the same, and you assume it's ohmic unless somebody tells you otherwise, and they wouldn't make you do numbers on something that's not ohmic. So we're going to try a problem here. It says a 6-volt battery delivers 5 amps of current to an electric motor connected across its terminals. Okay, so I'm just going to show you something here. A 6-volt battery. Okay, so the symbol for a battery is like this. Okay, this is the plus side, that's the minus side, so there's just a longer line, and a smaller line is the minus. And then I'm not going to worry too much about what the motor is going to look like, but the symbol for a resistor, and you'll see this later, is this ziggy-zaggy thing. I think just to make it kind of look like it's hard for charges to get through there. It's like, you're running a race and you have to like go around these cones, you'd slow down, right? It'd be hard to get through there. So they told us the voltage, and they gave us, the current, right? So they said that the voltage here was 6 volts, and there's 5 amps going through the circuit. So 6 volts and, half an amp. Sorry. 6 volts and 0.5 amps. And they're asking us to find how many coulombs of charge flow through the motor every minute. Okay? So this is not an equation asking for the resistance. We can find the resistance, but they asked us actually for how much charge, how many coulombs, right? how much charge is going by every minute, not every second, right? Every minute, so 60 seconds. So if we're going to go back and use this equation, I was defined as the amount of charge going by in a given amount of time. So we're solving for Q. This is a problem. We're going to multiply both. You can solve it this way if you want. Multiply both sides by time. So half an amp, right, times 60 seconds is going to give you half of 60 is 30 coulombs. Okay, so how many coulombs of charge flow through every second? 30 coulombs. I'm sorry, every minute. 30 coulombs go by in a minute. Okay, you could have done this as well. 0.5 amps is the same thing as 0.5. There's another zero in there. But coulombs per second, right? And then just multiplied by 60 seconds, or actually you would have started with 60 seconds probably, and then put the seconds down here and the coulombs up there. Half a coulomb in a second gives you your 30. Sorry. You could do it this way as well. 30 coulombs goes by. And then if we go back to, oh man, I don't think I ever switched it for you, did I? Rats. Well, sorry. Okay, so Q is equal, I is defined as Q over T. Q is I times T, so 30 coulombs. You could have also used a table to solve it this time if you know that amps are coulombs per second. Okay, and then the last question we will do here is, what is the resistance of the motor? Okay, so they already gave us delta V, and they already gave us I here, the voltage and the current. So if we go back to the paper here, delta V is I times R, and 6 volts equals half an amp times I don't know. Okay, and then we're going to divide both sides by half an amp. And then we're not, a volt over amp is an ohm, but 6 divided by a half is 12. And this is true if our motor, I'm writing R for resistor, if our motor is the only thing in our circuit, which I think we're assuming that it is. Okay, so that takes care of all of those. That's more than a normal class period would have. And I've taught a number of this stuff before, but now you've got a paper you can write it down on, and something you can look back at, and that should take care of that whole paper.